It's 10 o'clock, and we will have our first presentation now. Mr. Bénézech from France will give us an introduction, oder wird uns eine Einleitung geben zum Thema Hygienic Design und auch vor allen Dingen mit Schwerpunkt Biofilm, was da zu machen ist, wie man damit umgehen kann. Und dann werden wir noch eine Vorstellung haben vom Herrn Duculot. Danke sehr, ich bin in Französisch etwas schwach, aber das hat dann doch noch geklappt. Er wird uns auch zum Thema Biofilme einführen und vor allen Dingen eine Methode vorstellen, die also in der Lage ist, Biofilme auf eine sehr effiziente Art und Weise zu bekämpfen. Ich hoffe, Sie werden hiervon einiges mitnehmen und ich frage Sie jetzt schon, überlegen Sie sich Ihre Fragen, die Herren sind gewappnet. Vielen Dank, Herr Bénézech. Sie dürfen auf die Bühne und dürfen Ihre erste Präsentation geben. Mikrofon ist da oben. Ein Pointer? Ja, müsste ich. Ach so, ist da? Okay, alles klar.
Okay, guten Tag, Damen und Herren. Ich habe Deutsch gelernt, aber entschuldige mich, meine Präsentation will in Englisch. Ja. I will continue so in English. And my talk will be on bacterial adhesion and biofilm development, but I won't go into too much detail in microbiology. I just want to show some strategies possible to tackle this issue in food processing lines. So based on different examples. I'm coming from a laboratory, National Institute for Agricultural Research in France. And this is a small research unit in the north, very north of France, not far from Germany. And this work is a collaborative work with some universities and some other research institutes. So for the rational objectives of this talk, of all this work, of course, biofilms are considered to be major issue in the food industry and of course in beverage industries. And I would like just to show an example of a biofilm here. You can see here you have bacterial cells, and around these bacterial cells you have a slim layer. It's polymers excreted by the bacteria. May I have something to, because I feel blocked here. Okay. It's work? Okay, it's working. Okay, thank you. And, but what you can consider that this structure could be resistant, and it is in fact, could be resistant to cleaning, of course, for example, cleaning in place procedure, and could be resistant to heat, could be resistant to mechanical action, could be resistant to chemicals. And in these biofilms, you can have other form of bacterial cells, which are considered to be highly resistant, I should say spores. This is not for all strains, but this is a case for Bacillus strains, which is well known for the dairy industry. And these resistant bacterial cells are known to attach strongly to all kinds of surfaces and to resist to heat. It's not because they are in a biofilm. They just, even if they are alone on a surface, they can resist to heat, to chemicals, and to mechanical detachment as the flow of fluid on the surface. And to go further, these spores can be present in biofilms. in the laboratory, we work with Bacillus biofilms, and after some hours, it's possible to have almost 100% of spores in the biofilm. So this is why I wanted to insist on that, and I will show you some examples where we work with this bacteria in order to assess cleanability, cleaning, and different aspects of hygiene. So sanitation in the food processing line, of course, aim at removal of all the soil from the surface and aim at to complete elimination. We expect that complete elimination of the microbial contamination. And here in my talk, I would like to give you some elements, some ideas how to tackle these issues through preventive action and curative action. Preventive action, I will give you some example on hygienic design, and I will refer to the EHEDG, European Hygienic and Engineering Design Group. You have a booth of this EHEDG foundation, and the chairman is a vice president of the, or secretary, the chairman of, okay, of the German group. Yes, sorry, and curative, and for curative, I will give you example on cleaning and sanitation. So let's go. Just a slide from my colleagues from Camden, BRI in the UK, and explaining that for an equipment, if you want to imagine what could happen for this equipment, life cycle of this equipment during 20-year life cycle, for example, will produce 2 billion meals. What does it mean? 250 employees on how to clean, to be trained, introduce and train 80 production supervisors, spend up to 33,000 hours cleaning it, and some cost has generate 20 million euro of inedible waste. And proactively, what we will need for that, in order to mitigate that, it's the first thing is to redesign, to improve effectiveness, to educate management on risk, to spend capital to reduce risks, and redesign to improve cleaning, and redevelop cleaning procedures. So it's why I will give you some details on these different aspects. Thanks for John Holler from Camden. Hygienic design. What is hygienic design? If you look at the legislation, of course, in the EU Council Directive 2006/16/EC on machineries, it's written, machinery intended for use with foodstuff or with cosmetics and pharmaceutical products must be designed and constructed in such a way as to avoid any risk of infection. But that's very general. This is a law, but we have to go in further details. Another regulation referring to materials and articles intending to come in contact with food. They shall not transfer, sorry. It works. Yes, here. I'm stupid. Okay. They shall not transfer the components into the food, of course. This sounds to be obvious. But for the details, there are some norms, standards, where you can find the necessary details. And the first one is EN 1672 on food processing machinery. And you have details on materials of construction, surface finish, joints, and so on, related to food processing line equipment. And there are some, in this text, there are some examples of good design and bad design. But this is not exhaustive. In the international standard, ISO 14159, there is another approach which is based on a risk analysis. It means that for an equipment, the hygiene risk is dependent on where the equipment will be used in the factory. If it's at the entry of the processing entry in the factory for raw materials, the hygienic requirements are not the same as in the other part of the industry, especially for in the aseptic area and so on. Just a word on HDG. There are guidelines proposed by the HDG on their website. Some of them are free of charge. The others are for not a high amount of money, provided you are part of this European group. And in these guidelines, you will have full of details and interesting, important details on hygienic design and how to take into account the risk. And for the last, just a word on the FDA regulation, because FDA regulation is widely used, and of course it's necessary, it's obligatory when you want to sell your equipment in the US. So what is good hygienic design? What is related to? Hygienic design is related first to safety. Safety is to prevent the transfer of hazard, of producing a product without unintentionally adding anything to it. The second point is efficiency, facilitating cleaning in an economic time frame. And the third one is quality, maintains product in the main production flow. This is really important for fresh cut food industries, for example, but it could be important for beverage industry. Hygienic design. It's a multi-scale approach. If you look at biofilms, this is my only slide on biofilms. I hope you won't be deceived for that, but my colleague will give you some more details on how to tackle biofilms by using clean green detergents, and you will have more details on biofilm. This is a biofilm of Bacillus cereus. You see, after 48 hours, there are orange cells, and these orange cells are the living cells. These cells can be divided, can be grown. And here you have green cells, and these green cells are spores. You see, there is a significant amount of these green cells after 48 hours. Here is a 3D structure of the biofilms. So you can have, it's not a homogeneous layer on the surface. It's something which has rigidity, but it's not as a solid slim on the surface. So, however, it doesn't mean that it's very easy to remove. Most of the cells, maybe the cells here, can be removed quite easily. It could explain cross-contamination of product. However, the other ones are quite difficult to remove without any, for example, without any detergent or any mechanical action. If you look in a microscope, electronic microscope, the bacteria, you see this bacteria and attach on the surface, and you see here a specific structure of the surface of the bacteria that could explain the attachment on the surface. So what can you do with that, with this situation? Of course, microorganisms growth after cleaning and disinfection could be related to a poor hygienic design. And poor hygienic design, as this one presented here, here you can have a blockage with some soil, not removed, and appearing to be a protection to these microorganisms. I said that it is a multi-scale approach, multi-scale topic. So if you look at the surface, a parameter widely used by people and this parameter, you can find this parameter in lots of standards, is the average roughness. And in EHEDG, it is considered that the threshold value for food equipment, food processing equipment, is 0.8 micrometers, RA. Here it's just a small drawing showing the bacteria, and bacteria with their specific structure of the surface and the different size that could be seen on, for example, on stainless steel. And when you can imagine here that there could be protection of the bacteria. In the reality, it is not as simple as that. Here you have example of different surfaces. Here it's the same average roughness of 1.5. 1.5, it's not good. And if you look at the HGG guidelines, it's not good. However, we found that this surface was better cleaned, was easier cleaned than a flat surface with an average roughness of 0.05. So what does it mean? It means that there is another parameter that could interact with the surface topography. It's environmental condition and the flowing conditions. And here, the flowing conditions were favorable at the wall, were found favorable to the removal of the bacteria. You see. So just to explain that it's not that simple. Of course, here it was the worst case. And you can imagine why it was the worst case. Here, it's another example of a surface with a nano pattern on the surface. And you see the spores, as I shown on the previous slides, and you see how the spores could attach on this kind of surface. You see what the bacteria can see when they are on the surface. And what was observed here, it's that it's possible by this nano pattern system to induce attachment, to enforce attachment, and to reduce attachment. However, in the food industry and in food equipment, you can imagine that this nice surface could be jeopardized by the presence of proteins or food elements that could enter inside. Molecules can enter inside the system, and the good effect could disappear. Here it's other parameters that you can find in other kind of industries, in wearing industry, for example. And this parameter we found in the laboratory that they are the reduced value of peak depth, integrating the fact that they are deep depths or high peaks that could interact with cleanability. And we found that the depth of the valleys were extremely important to take into account in order to define hygiene. So the average roughness is not sufficient, but it could be considered as a good parameter, but not sufficient if you want to go into details. If you want, for example, to find the best surface for the best objective, has low attachment, for example. Surface topography is important and could explain, of course, the fact that metal-to-metal contact is forbidden. And it's why we have to use gaskets in polymer. Hygienic design is also, of course, macro scales. Macro scales doesn't mean only equipment design, but mean the factory design. And I won't go in example on factory design. There are some good books published by people from the HGG that would head the publications that could be available to have these details. I just give you some example on equipment design. On equipment design, what's important, it's first could be the welds. And good welds, bad welds, you can imagine that here it's a bad weld. But welding is preferable to fastening, and here it's a case. There an example with fasteners, and this is considered to be forbidden, has not to be in the equipment system in contact with food. Something very important is to be sure that water after cleaning and disinfection is removed from all the processing line. If you have water, you can have bacteria growth. Bacteria need water to grow, or moisture to grow. And here it's the case, in the case of a hose system fitting, and they are good hose system fitting and bad hose system fitting. Here it's something you can find everywhere. It's reducers at the entry of the equipment, at the exit of equipment, and especially you have lots of that in skid system. And of course, they are bad or good design. And here you have, the drainage is bad. Here it's due to the fact that the flow inside, when cleaning, the impact of the flow will be different here and here than here. I will give you the example when I will say some words on cleaning. The last slide on hygienic design. Please go to the EHDG guidelines. This is the radius curves. And the radius curves here, of course, 90 degree, it's not bad. It's bad. What is recommended is this case. Some words on cleaning. Example on assessment towards actions. In the lab, we decided to work on the evaluation, on the assessment of hygienic design of all kinds of equipment encountered in the processing line. Here it's an entry ball of a surface scrape heat exchanger. And you can see the entry ball, and you can see a lot of holes in it. It was to install probes, and these probes, probes, were for measuring the shear forces at the wall. Why measuring the shear forces? Because we look at the effect when cleaning of the flow on the removal of bacteria from the surface, and how to measure the bacteria, the remaining bacteria inside the system, so complicated system. We decided to work with a method not far from the method proposed by the EHDG. It's a multi-method method. You put nutrient media, solid nutrient media, inside your system. You have a sort of cake. And you contaminate your equipment first, you clean, and you look at the remaining contamination. And the areas where the remaining contamination is high could be considered as poor areas in terms of hygienic design. Here you can see the colonies of the bacteria from the bacteria remaining on the surface, and these colonies appeared yellow, not yellow, it's the nutrient media, yellow, appeared red because of the use of tetrazolium chloride used for the respiration of the bacteria, and you have a change in the color. So the colonies appeared red, so it's possible to count quite easily the colonies on the surface. So it was possible to compare the amount of bacteria remaining on surfaces and the shear forces measured. Here it's a case of two-way valve cleanability. You see there are different areas characterized by different colors. The green color, not a lot green color, but I don't want to say it's a really bad design, but it was possible to differentiate in between all the areas of the valve between what could be considered as highly good or or bad or less good. Based on the measurement of the shear forces, what we found that the average value of the shear forces, of the mechanical action, the average value, is not enough to understand the removal. What was more important are the fluctuation of the shear forces. And why did we have fluctuations? Because when cleaning, you have a turbulent flow, and you have ADs, turbulences inside your system. So at the wall, you have fluctuation of the shear forces when cleaning. And the higher the fluctuations are, the better the cleaning is. So it means that some areas which are considered to be for the mean value of shear forces quite low can be easily clean, can be really clean because of this high fluctuation observed. So it's important to see that in order to not to remain at these mean values as I explained for the topography. Another example is the potency of recontamination when cleaning of the equipment and how the design could interact. Here we install in processing line, very simple processing line, highly soiled pipe and clean pipes. So that's normal. If you want to clean something, it could be very highly soiled. So this is not a surprise. But what was a surprise was the observation when cleaning of recontamination kinetics of the rest of the line, and especially on the clean pipes. And we decided to look at if the bacteria has an effect, the kind of bacteria used could have an effect on this recontamination presence. And there were 3 bacteria used, 3 strains of Bacillus, and looking at in the different location of the processing line, which bacteria are recontaminate or highly recontaminate or poorly recontaminate. What was more interesting to see is that 2 things. The first thing is after a band, the recontamination was found higher. So it means that the flow inside the system, the changing in the flow due to the band, will induce the recontamination, will favorite the recontamination. And we worked with a valve, a mix-proof valve, and what we found is the design of the valve could have an effect on the recontamination effect. So just to say that when cleaning, it's possible for this kind of bacteria, it's possible to see this recontamination, and hygienic design has something to do in lower mitigate this phenomenon or higher this phenomenon. One of the explanation of that could be how the flow is organized, how is the flow pattern. When cleaning, there is a turbulent flow. So turbulences, I call that ADs. I don't know if you understand this word, ADs. And the size of the ADs, we looked at the size, we recalculate the size of the ADs based on the measurement of the spectral densities of the velocity. And what we found is the smaller the ADs are at the surface, the higher is the deposition of the spores. And we found, we try to find some explanation on this redeposition phenomena based on the environmental condition when cleaning and based on the organization of the flow. So the question is it possible to calculate that? Because if flow is important, why not calculating that? There are some tools available now on the market, CFD, computational fluid dynamics tools that would be of help in calculating how the flow is organized inside the system. But what's important is which model, because it's possible to calculate everything based on the equation, physics equations. But this is more for aerospace industry. They have lots of money, and it will be more difficult for the food industry. So we use models, but these models are not too bad, not that bad. And with the technical center in France, we try to evaluate different kind of models for the CFD calculations. And what we found, it's one of them was quite good to recalculate the values observed of the wall shear stress of the mechanical action. So it was possible to have the purple line was found to be better to explain this point than the red line. So it was possible to see the effect by calculation of a rubber seal bulge. It was not well fitted. There were a bulge of 1 millimeter, and the consequences were seen on the bacterial removal, but it was possible to evidence that by calculation. So why not trying to redesign based on calculation and based on the experiment, on both experiments and calculation, to redesign some parts, not all equipment, but some part of the equipment, using this calculation tool. For the flow conditions, of course, fluctuations were found to be good, interesting, important for the removal. So the idea was to work with a pulse flow system. We tried to change, to have the same mean velocity compared to the steady-state system and fluctuated system with the same mean velocity. What we found? We found that with a similar wall shear stress, mean value of the wall shear stress, we found that there is an improvement in the removal of the bacteria comparing to no pulse system. But if you maintain the mean velocity, it's possible to see the improvement, but it's possible, of course, to have an optimal in using the right frequency and amplitude of the pulsation in order to mitigate the remaining contamination. What's more interesting was to find that the removal kinetics was totally changed with pulse flow comparing to steady state. There are some ongoing work in Germany now, in a partner of ours, in Braunschweig Technical University, and they are more recent work. Our work were published in 2009, and there are some work published in 2013 from this university, and we are working with them through a European program at the moment, and using these techniques within other kinds of other techniques. So, conclusion. Yes, it's more than 30 minutes. Just let's go to the conclusion. What was important to show? It's to show that are the mechanisms involved in the removal of various contaminants, and through understanding the role of surfaces and geometries, integrating kinetics aspect. I show some on the last slide kinetics of the removal. It's important to have a view of the kinetics, if it's rapidly removed or not, and in order to define the longer of your cleaning time. to minimize recontamination, cross-contamination, to identify new flowing conditions when cleaning, to redesign new materials, what is the best surface, what is the best topography, for example, and to reformulate new detergents. So I will let my colleague presenting something about green detergent. And improvement necessary to model flow impact. This is something we can go further there. I think we can have a good tool for designing. And the last point, what is mandatory for me and for the EU is how to lower sanitation and environmental impacts, because it's really important today. It's less important that the hygienic level is quite good, could be considered quite good, but the environmental impact has to be improved. And maintaining this hygienic level, but lowering environmental impact is an issue today. Thank you for your attention. Herzlichen Dank für Ihre Aufmerksamkeit.
Yeah. So, if you need translation from German to English, please get your earphones in the back. Otherwise, I will change to German now. Are there any questions? Sind da irgendwelche Fragen, die Sie haben? Ich habe schon mal eine Frage an Sie, da können Sie sich das schon mal überlegen. Wer von Ihnen kennt die EHDG noch nicht? Sie sollten hier nicht vom Stand weggehen, ohne die EHDG zu kennen, weil das ist ein ganz entscheidendes Kriterium. So EHEG is one of the key elements in hygienic design, and you should know EHEG. And the people who don't know EHEG up to now, they should get to know EHEG. Otherwise, you can't prevent any problems. I know that. So your question, please.
Ich habe eine Frage zur Oberflächenspannung. Entschuldigung, zur Rauigkeit. Eine Frage zur Rauigkeit.
The surface properties, you mean the... The roughness, yes.
Wenn ich richtig verstanden habe, hatten Sie gesagt, beim RAS-Wert von 0,5 ist die Reinigung schwerer als beim RAS-Wert von 1,5. Ist das richtig?
Yes, I understood most of that. You mean 1.5? 0.5 comparing to
1.5.
0.8. Yes, I think on the EHDG point of view, it's 0.8. I never see any difference in between 0.5 and 0.8.
Okay.
So based on the experiments, all the experiments we run in the lab with microorganisms, with spores, with biofilms, and so on. This is what has a real impact are the defaults on the surface. You can have a very smooth surface with big default, with scattering defaults, and these defaults are important, you see. So the mean value doesn't represent anything. Of course, it's a guarantee that the big defaults or the main defaults are not that huge or not that numerous on the surface.
Nevertheless, it's more the topography which makes the music and not the roughness. So you really have to take care for that. So you had a question? Maybe you come over here.
Thank you. Yes, Thierry, excellent presentation. Rob Beale from Syngenta in Cambridge. We're interested in biofilms in domestic appliances, and we've been researching electromechanical ways of disengaging or separating the biofilm from surfaces. Have you investigated anything like ultrasound or those kind of mechanisms?
In the lab, usually to remove bacteria from surfaces, we use ultrasounds. And now we are working with SME in the north of France within a European project, providing ultrasound feature systems in order to remove biofilms. And so we trust that it's for the future, it could be a good opportunity. We are still in the progressing in this topic, but I'm sure that it will save not for the whole system. I think it's these alternative methods has to be used for defined areas, critical areas, and not for the whole system. Okay, so it's good. Thank you for your question.
Any other questions linked to that topic? Okay, there's another question.
So, can you hear me? One of the last slides, your experiment with the fluctuating cleaning. What was the maximum velocity applied during that? You said in average you were below the 1.5 meter per second.
Yeah. So we up to 3 meters, 2 or 3 meters. I think as far as I remember, it's 3 meters per second. Yes, this is quite high. And for our pilot plant system, of course, it doesn't sound too high, too big. But for the industry, it's quite high. Usually they use 2 meters per second or 2.5. But 3 meters, it's quite high. But what we wanted to show that it's this change in the velocity has an effect at the wall, which was not obvious at the first. Because the size of the perturbation I explained first, and the size of perturbation by the pulse flow are not the same. It's a different scale. But the effect at the wall, at the bacterial size, is real, is actual. So.
Any other questions? So my question was, who knows EHEDGE? Who doesn't know EHEDGE? The rest? Okay, so you should know. We have a booth over there. EHEDGE is taking care for hygienic design, and we are developing guidelines on the topic of hygienic design. And to prevent Biofilme zu verhindern, to prevent biofilms, it is necessary to have facilities which are cleanable at first. And if they are cleanable, you can remove, for example, biofilms. You can even prevent biofilms in a certain way. And so you should know how to design, wie solche Anlagen zu entwickeln sind, wirklich solche Sachen effizient in den Griff zu bekommen. It's always a matter of efficiency. And efficiency is always connected to money. So that's why we have to make our facilities cleanable at first. And then we can also prevent biofilms and we can clean them.